Well, good morning, or it's afternoon. Thank you for the invitation to come and talk about my hero, inverted commas. As you said, I went to Manchester many years ago, 1945, as an undergraduate. Blackett was there, so I knew him for all the rest of his life. But you must remember that no man is a hero in the eyes of his valet. And I was his valet. So, you may find one or two things slightly disagreeable. Never mind, that's history, as it is. Not that it shouldn't. I thought I'd better say a few words about his pre-cosmic ray work, because I note in the programme there's rather little for Blackett, rather more for Eddie Bullock. He was born in Kensington in 1897, and I must point out that a great-grandfather came from Hamsterley in County Durham. I had to get Durham in on the act somewhere. 1914, he joined the Navy. 1915, he fought at the Battle of Jutland as an artilleryman on HMS Barham, and that influenced his knowledge of statistics and his obsession with accuracy. In 1919, he came to Magdalen College, Cambridge. 1921, he got first in physics, did research, as we've heard, under Rutherford, who had arrived at Cambridge from Manchester 2 years before. And I think a lot of what he did, certainly in cloud chamber physics, he owed to C.T.R. Wilson. And indeed, in his Nobel lecture, December 13, 1948, referring to C.T.R. Wilson, who was here, I, like all the other workers with the cloud chamber the world over, are indebted more than we can express to his shy but enduring genius. And he really was in that category. The first topic he was given by Rutherford was to use Shimizu's cloud chamber, small cloud chamber, and fire alpha particles at nitrogen. 1924, he observed the first disintegration and also the synthesis of a heavier nucleus. So in a sense, he was the first to observe the transmutation of the nuclei, and that was nitrogen-14 plus helium going to oxygen-17 plus proton. March 1924, he went to Germany, where he worked at Göttingen with Frank and Hess playing. And then, something happened which really turned him on, and that was 1932, when Beppo Occhialini arrived from Italy. Apparently he came for 3 weeks, stayed for 3 years. And he brought with him ideas about cosmic rays from Rossi and others, and that really turned Blackett on. Well, what I thought I would do is just go rather quickly through the discoveries he made, and then go back to look at one or two of them from the point of view of what the situation is in our understanding, or lack of it, at the moment. So, So he was in Cambridge 1919 to 1933, 32 Occhialini came, and between them they devised this counter-controlled cloud chamber. Now Blackett was, and he admitted it, one of his many attributes, at any rate, he was a mechanic. He loved apparatus, playing with instruments one sort and another. And between them they devised the counter-control cloud chamber. And this was a device that not only improved the efficiency of the cloud chamber for detecting cosmic rays, but allowed events of great complexity to be selected. But it's amazing that, in fact, the positron had been discovered just a few weeks before Blackett got round to that, looking up doing it by Anderson, 1933, using a cloud chamber and random expansion. That was lucky, wasn't it? To get one of these ultra rare tracks, just popping the cloud chamber pop around. So he missed the positron, but confirmed it. He was very, very interested, here, very interested in the cosmic ray energy spectrum, or momentum spectrum. And we'll see some examples of the tracks that he measured with such accuracy shortly. And he realized early on that the energy spectrum of these particles went way, way, way beyond the energies achieved by radioactive nuclei. In a sense, it seems to me, that had Occhialini only come a year earlier, here we go again, Blackett would have been the first for this, the first for that, the first for the other. As it is, his valet reports he was second for this, and he was second for that, and second for the other. Never mind. In fact, to remove to Manchester in 37, but as early as 1932, there's a mistake. That should be Blackett and Wilson. The Wilson at A should be an and. The Wilson is John G. Wilson, who had graduated as a student of CTR Wilson, an expert on cloud chambers, and they found that the energy loss of some of the particles travelling through a cloud chamber, which had metal plates in, the energy loss was too small compared with what had been expected for a proton. The particles were not electrons either, and this led them to appreciate there was another particle of intermediate mass called the muon, mass about 206 times or 207 times the mass of the electron. And they identified that just after Anderson and Nevermind. Again, that bit too late. Never mind, Blackett was a keen worker. He showed in 1938 the so-called temperature effect of the cosmic ray intensity, which was to do with the fact that as the air heats up, the atmosphere heats up, the production level gets higher, and of course that related to the decay properties of the atmosphere. He showed in a rather elegant way, although he wasn't unique in this, that the Lorentz transformation time was valid. Otherwise, we would not see any cosmic ray muon at all. The muon was found to be unstable with a mean lifetime of 2.2 microseconds. It should not arrive from a height of 20 kilometers or 15 kilometers or whatever it produces at ground level, but it does because of the Lorentz transformation, the gamma factor that comes in to the simple Einstein theory. During the war, it's a well-known story about his work with remotely, mainly with Lovell, which led to eventually to the idea of using radar reflections from cosmic ray showers in the atmosphere. It led to Jodrell Bank and radio astronomy. And then Manchester again, back after the war, 45, 53. He worked with his juniors, Rochester and Butler, discovered the beacon. And that was perhaps, point of view of many, I think it's true, it was the most important observation that was made. Imperial College, from 53 to 74, he worked as well as important work in geophysics, and geo, this, that, and the other, who worked on the cosmic ray policy. Right, well, let's just have a look in a bit more detail at some of these topics. Blackett was interested in astronomy. He was interested in everything, in fact, but particularly interested in the sun, and we know the story, and we'll hear from Frank Wells in more detail later about his interest in the magnetic field of the sun, the dipole field, the other field of the sunspots, and so on. He was fascinated, and he came up to Durham on one occasion when I told him that the differential rotation of the sun had been discovered by Richard Carrington initially in Durham before he, in the 1840s, before he left and went to Red Hill in Surrey. And he was interested in the fact that we in Durham had just, that's late 60s, early 70s, not long before he died, we in Durham had decided to go into conventional astronomy in as big a way as we could manage. He was interested in the Cherenkov radiation. He realized that the energy density of the Cherenkov radiation produced by cosmic ray electrons in the atmosphere, traveling faster than the speed of light in the atmosphere, was about 10 to the minus 4 of starlight. In other words, one could never get a perfectly black background. There's always the possibility, well, the fact that Cherenkov radiation was occurring. Let's look at the positron for a minute. Can you see it? It's a track.
Press the red button in the top.
Sorry, that's pushing on. The track coming round here and coming up here. Why it's so faint here. Anyway, this is Anderson's first unambiguous evidence for the existence of a positron. A particle on a random trigger is moving upwards, penetrated this plate, and was curved again in the magnetic field here. And the fact that it's the curvature here has a radius smaller than the curvature here shows partially moving. Why did Blackett not see that? Well, as I mentioned, he was a bit late into the fray, but he once told me, I think it's true in fact, that he'd seen one of these tracks moving upwards, and he thought the field was the other way. Because in those days, you run the cloud chamber automatically, taking photographs, flashing the light and all the rest of it, and then develop the film. And every day they would reverse the field to try and reduce systematic errors. And on this occasion, he'd seen this wretched thing and thought, oh, the field must be the other way. Tragic, in a way. Antimatter, first demonstration of antimatter. As you know, the problem is still with us as to what happened to all the antimatter. Only 10 to the minus 9 from that produced in the Big Bang is still with us. So there's still a lot that we don't understand. I've mentioned this already. Invention of the counter-control cloud chamber, existing positron. In a sense, he detected cosmic ray showers, and here's a rather nice photograph that he and Occhialini took in 1933, and you can see the tracks bent in opposite directions. In other words, whichever way the field is, there's some plus and some minus. So, and he correctly diagnosed, or him, not me, that it was photons, not neutrons, as it could have been, that were producing these showers, V plus and V minus. Here are some rather nice photographs, one that he took with John Wilson here. Another Wilson alone, you can see particle coming down and then losing energy and being deflected here. And Blackett's main contribution at the technical level was in fact in reducing the distortion that one often found in these cloud chamber tracks. And I know from personal experience just how keen he was on getting good cloud chamber technique. It's interesting. Blackett developed a technique for measuring the radius of curvature of the tracks very accurately. It involved a very small angle prism into which you sent the image of the track, and then this fell on the screen, and you squinted along the screen and rotated the prism. You put a straight line into a prism and turn it, it gives a curve, so you can compensate. And he developed this tremendously, and he measured many, many tracks, and poor old Wolfendale also had to measure even more tracks using this using this beautiful to such an extent that when I went up to Durham, I developed a squint. Literally. Nowadays, it would worth millions. I could sue Blackett. In those days, they wouldn't done. And I waited, eventually having it corrected by a surgeon many years later, because I was having to wear prismatic spectacles with thicker and thicker prisms. It was awful. Anyway, when I was knighted, the chap who did the operation wrote to me and said how delighted he had been not to find that I had discovered a new double galaxy. Otherwise, he said, both our careers would have been in ruin. Here's a picture of the Manchester group in 1949. There's Blackett, Rosenthal. Is that Clay? John Clay?
Yes.
Geophysicist.
Yes.
Clifford Butler, Lovell, Rochester, I think that's Harrelson, and Keith Rundle, and various other luminaries. Whenever I look at this, I always think about this man. Here. Bernard Hine, he was a year, 2 years ahead of me. He was operating a cloud chamber, and he got an anti-proton. One. And he didn't get any more. And he didn't publish. It's amazing that Blackett didn't insist that he published. Because as we should see, other events were published which were one-off. Anderson was published one-off. Something that historians, no doubt, I can see PhDs in this. Well, there are many, many others on there, but Frank will be talking more about here. The strange particles, discovered by Rochester and Butler in 1947, using a counter-control cloud chamber, and this is the event here, V0. The neutral particle came out of an interaction in here and decayed into two of known universally as the Rochester and Blackett discovery, but in point of fact, Blackett had a key role in this. It was Blackett's cloud chamber, which they'd been allowed to make slightly deeper, and Blackett, of course, taught them all they knew about technique, but more particularly, it was Blackett who was very, very keen on the interpretation in terms of new particles. So here you have this man who was willing to take a charge. And in fact, in his Nobel lecture, he goes into some detail about this. And Rochester himself has written and agreed that, in fact, it was Blackett really who was behind it. This is very important, because many say, well, why did Rochester and Butler not get the Nobel Prize? In a sense, Blackett got it. Thought at the timing isn't quite clear, it was right at the end of the period, but nevertheless, as I say, it's mentioned in his Nobel address. Blackett really was a great designer. So although he was second for the positron, second for the muon, he was first for the strange particles. So I think from that point of view, it's appropriate that he should have received the Nobel Prize. We haven't much time, but I'd like to mention this. If you look at the energy densities in the galaxy of a variety of phenomena, you find here starlight, Blackett pointed out, is about half an EV/cc, to be compared with cosmic rays, which were half an EV/cc. Now, as we know, he and others were very keen on these coincidences and trying to read important sort of discoveries into them. But he didn't go very far in this direction of saying, therefore, cosmic rays came from stars. It's almost certain that that equality is by chance. If you look at the magnetic field of the galaxy locally, it's about the same. You look at, we showed years later, gas motion. There's a lot of work on massive gas in the galaxy. We'd overestimated it previously. The average is about the same. And indeed, many use these equalities here, particularly between cosmic rays and magnetic field, because you can make a physical model there where the field traps the cosmic rays of the galaxy, and would let them out if the energy density cosmic rays were greater than the field. Some have said, well, this shows that the cosmic rays that we see are galactic in origin. This is one of the big problems. Well, they're universal. The cosmic rays for the whole universe. If so, enormous energy density. But the possibilities. However, with the discovery of the cosmic microwave background, it's the same within a factor of 2, that's universal. So it's a good example of how you've got to be very careful about these coincidences, the extent to which they are significant or not. Well, lastly, I want to talk about the energy spectrum of cosmic rays at the very high energies. As you can imagine, Blackett was very keen on the highest energies. I remember arguing, in a sense, as much as I can argue with his boss, that we bumped at a few 10 to 15 EV in the spectrum. It was just interesting that he was very, very keen on the highest end. And he was one of those who was very keen on the Havelock Park extensive air shower array, which was constructed mainly by the University of Leeds. Initially, John Wilson was the head, but after a few years, Alan Watson, who is here today, assumed the leadership, and they made one of the very first and best estimates of the energy spectrum. And you'll see this is energy cubed times the intensity, almost a kill law here, and then it suddenly, these other measurements tended to confirm it. There's argument as to what this is due to. I'm one of those who believe that this is the galactic particles coming to an end, if you like, and these up here are extragalactic particles coming in, and perhaps with a reduction caused by the interaction of the cosmic ray and a cosmic and microwave background. But the big project, the Auger Observatory, where again Alan Watson was co-leader, has confirmed this general shape much more precisely, and this comes down here. But this reduction up here may or may not be due to the interaction with the photons. Could just be that the sources run out of energy when you get to some very, very high value. It's not easy, we're not sure. The sources may be active galactic nuclei, we're not sure. And there's some problems about the mass composition at these very high energies. But the point I'm trying to make is that the cosmic ray work that Blackett and Powell and others in the UK started is still alive and well. Thank you very much.
Well, thank you very much, Sir Arnold. Any talk. Are there any quick questions? I'm sure there are many. One. There.
So, Sir Arnold, the experiment that joggled back to detect cosmic rays using radar famously failed. And my father, my late father, my name is Lachlan Together, used to say that it was one of the remarkable things about Blackett that's already been referred to, is that in the event of failure, he picked up whatever was going on and developed that. And you correctly said that then, of course, the echoes from the meteor trails and then things took on from there. Is it the case that that's still a failure, or can we now, using modern techniques, detect cosmic rays using radar as they enter the Earth's atmosphere?
Well, the radio technique is used to determine some properties of cosmic rays. This is radiation produced by the curvature of the particles in the magnetic field. Alan, next to you, knows probably better than I whether indeed showers have been detected by radar reflection.
I think the answer is that at the present time, no. Since the model Blackett attempts in the 40s, there was an attempt in Japan in the 60s, and without having one going on in Utah. There's not been any convincing detection.
Professor Lovell had done some very impressive cosmic ray work, in fact on showers with cloud chambers before Blackett, if you like, moved him off. It's a great one for moving people off. And he always said, well, when the cream is off, you move and do something else. So he always thought the cream was off in cosmic rays, that's why I moved into your subject. Yes. Incredible. I mean, very interesting.